Welcome everybody. So this week and next week we're gonna finish our proof of completeness, which that will finish the proof of compactness and we'll have everything wrapped up from the course. Let's remember completeness says that if you can prove if something is satisfiable. So it's if completeness says that if you have a set of sentences semantically or logically implies a formula phi, meaning that in every model of gamma satisfies phi, then there exists a proof from gamma of phi, right? So if something is true in every model, then you can actually prove it in a formal way. So you can find a finding deduction satisfying those model exponents and just the axioms that proves phi from gamma, like formal proof. And so we saw already how this implies compactness, and therefore all the applications that we saw before follow from here. And we saw also that this statement up here is equivalent to the statement number 2 that says that if a set gamma is consistent, it is satisfiable. So consistent means that you cannot prove any contradiction, right? Right, so there is no deduction from gamma that implies a contradiction. That's what consistent means. Satisfiable means that there exists a model for gamma. So if you think about it, proving this is going to have to be hard no matter what, because our assumption is that there is no proof of a contradiction. It's a very combinatorial syntactical assumption, like there is no finite set of formulas which satisfy model exponent and the axiom such that the last one is a contradiction beta and not beta. It's purely syntactical and just manipulations of symbols. This is just about manipulations of symbols and something not being possible. While this one is about there existing a model. So some way we have to, out of this hypothesis and out of a set of sentences, create and build a model for it. So that's going to be the task. So for today, we're going to start that process of building the model, which we're going to finish next week. It'll be 2 short weeks. And we're going to consider this thing today, this set of terms, and later we're going to consider the term model for a set of sentences. Okay, so let's start with a vocabulary tau and a set of sentences gamma, which we're gonna use like all throughout these videos. So we start by defining these sets called A. It's a funky A. It's an A. Enderton uses that one to be the set of all closed terms. What does it mean to have a closed terms? These are terms without variables. So let's review what that is. So what do we have in this term? So if C is a constant symbol, C is a closed term. If F is a function symbol and has some arity, let's say n-ary, remember that means that takes n inputs, and T1, Tn are closed terms, then we get that F parentheses T1, comma, T2, comma, T3, comma, all the way up to Tn parentheses is a closed term. Okay, so these terms are built out of constants by applying the function. But let's remember, this is when I say applying, it's not really applying, because these terms are nothing more than just strings of characters, strings of symbols from our vocabulary. And in this case, the symbols are only the constant symbols, the function symbols, and the parentheses, and I guess the commas. You don't need the commas, actually, but we can put the commas. So there are strings of symbols. So when I say apply, I don't really mean apply. What I mean is you write a new string of symbols that has the function, the symbol for F, the symbol for parentheses, then the whole string of symbols for this term that you built before, then the comma, then the whole string of symbols for that term you built before, and so on, and ends with closed parentheses, and you get a new string of symbols. So here is for n-ary functions. Remember, there are 1-ary functions, 2-ary functions. So those are the closed terms. So they are exactly like the terms that we defined before, except that we don't allow variables inside them. Okay, that's the definition of this funky A, set of closed terms. Then we are going to consider this thing. E is going to be a binary relation on this A, on this set A. It's going to be the set of pairs of closed terms such that gamma can prove, like formally, with a formal deduction, that this one term is equal to the other. Okay, so these S and T are also strings of symbols, they are terms, and these just consider the pairs such that gamma can prove that they are equal. Okay, so sometimes we are going to write, in this case, we are going to write S, E, T to mean that S, T belongs to E. Okay, because it's a binary, it's a set of pairs, we're going to use it as a binary relation, so we're going to write S-E-T for that. It's a purely syntactical definition, right? So this is saying there exists a finite formal deduction of this formula out of this set of formulas. Okay, so we have a term, we have a set of all closed terms, we have a relation on it, and we're going to be looking at this thing, which is the quotient. Remember, when you have an equivalence relation, which we're going to prove later in this video, that this E is an equivalence relation, we can take the quotient. The quotient means, like in here, the quotient means just take the set of all equivalence classes, right? So this is nothing more than the set of all equivalence classes according to the equivalence relation E. Okay, so just essentially, when you take a quotient, what you're doing is making all things that are equivalent kind of equal, in a sense. So before we get into this further, let's look at some examples, and hopefully this is going to clarify what's going on. So let's look at this example. Let's suppose that tau, our vocabulary, contains a constant E, a binary operation star, like usually when we do groups, and an extra constant C. Okay, so we have constants and a binary function symbol. And let gamma be the group axioms. Okay, we have talked about them a few times. Essentially, they say associativity, the existence of inverse, and that E is the identity. Okay. So those are the group axioms. So let's see what happens when we do this construction in this case. Let's go step by step. Let's first consider this. I don't even know how to draw that. I want to draw it like that. Set of closed terms. So it's hard to tell them all, but let's just write a bunch of terms that we have. So E is a term. C is a term. What else do we have? E star C is a term. E star C star C is a term. E star C star E star E is a term. And you guys get the idea. Anything that you can build out of these operations is a term. Use what? Only operation is this star. You can put things together and you can get things that are very large. Essentially, for instance, that term, anything. So you can get very big terms. So this set contains, this A contains all the terms you can write that have no variables. So that means you can only start from these constants. In this case, there are two constants. You start from them, and then you apply the functions. You get all these guys. Okay, so far they are just terms as strings of symbols. And then we are considering this equivalence relation, which says that two things are equivalent if and only if, or are E related if and only if they are, gamma can prove they are equal. So let's start, for instance, with C and C star E. Do we have that these two are connected, that are related via E? Well, let's see. Yes, why? Because gamma can show that for every x, x equals x star E, right? That's kind of the identity axiom. Maybe you have to flip, or you have to do something, but you can prove that from gamma. And then if you prove that using the fact that one of the axioms, that if you have for all, you can change it for any term that you want, you also get that gamma can show that C equals C star E. Right? Let me just do one intermediate step right there. From there, you get that gamma shows X equals X star E, where X is replaced by C for any term C, in this case just C. And then so that means that gamma shows C equals C star E. Okay, so that gets you that these two are equivalent, and that's good, because if you are talking about groups, C, anything times E should be the same as C. So this equivalence, that's what it's saying. Kind of these two should be considered the same. What about, let's do another example. C star C star C is irrelated to C star C star C, with a parenthesis on the other side. And again, why is that? This is a true. Yes, that is true. And the reason is yes. And the reason is that gamma can show that for every x, x star x star x equals x star x star x, if you put the parentheses on the right places. And from there, again, using one of these logical axioms, we get that gamma shows that C star C star C equals C star C star C, with the parentheses in different places. And therefore, that's why you get that these two are irrelated. So that's pretty good. So that's looking like it's like a group. So what are the elements that we get then? So let's see now if we can understand what this quotient. Yeah, so let's try to figure out what that's gonna look like. So let's think about it. So I claim that whenever you have a term, let's say like this term up here, then you can transform it into one of the form, let's put it up here, C star C star C star C, with all the parentheses towards the left, and the same number of C's, 4 C's, and no E's. Right, and that's because we know from the previous two things that, well, gamma is going to be able to prove that those two are equal, because gamma can show that E is identity and can show associativity, so allows you to move the parentheses whichever way you want. So gamma can show that these two are equal. So essentially, all the terms are going to be of that form. So what we're going to get is that m gamma, this quotient up here, is equal to, well, you have the equivalence class of E, and this bracket here means equivalence class. Remember, we're doing a quotient. So equivalence class means put everything that is equivalent to E as associated and put it in a single bag, kind of. This means a set of everything that is equivalent according to E. And then you have the equivalence class of C, and then you have the equivalence class of C star C, and then you have the equivalence class of the term C star C star C, and then you have the equivalence class of C star C, and so on and so forth, right? So those are all the terms you can write. I mean, at least every term is equivalent to, according to this E, to one of these. Every term you can prove that is equal to one of these guys, either C or C times C or C times 3 times, 4 times, 5 times C. So those are all the terms. So that's what this quotient looks like in this case. Good. So that's what it looks like when you associate everything that is E is related according to E. That you can prove that if you can prove that it's equal, you can make it equal. That's all you get left. Do we get a group? We started with the group axioms. Do we get a group? And no, we don't get a group, right? There is nothing that is the inverse of C, let's say. So C has no inverse in this structure, in this in this set, in this quotient, right? Because like when you multiply two of these guys, so if you multiply something that has like 2 C's and something that has 3 C's, you're gonna end up with something that has 5 C's, right? So when you multiply, you're just adding the number of C's that you have in there. But there is no negatives. There are no negatives, so you don't have an inverse. You cannot get to E in this structure. So it's not a group. These things are called monoids. I don't know if you've seen them. So it satisfies associativity and it has an identity. So that makes it a monoid, which is short of being a group because it doesn't satisfy the inverse. So the inverse axiom. So because there are things that have no inverses. We cannot build a term. We don't have a term for the inverse if this is our tau. So one way to fix that is to consider now this example. And let's see what happens. So in this example, we now have two constants other than E, the binary function symbol, and also a unary function symbol right there. Okay, so we are adding now an inverse as a function symbol that you can build terms with it. And okay, when I say the group axioms, I'm gonna imagine the group axioms that refer to this inverse, right? So the group axioms say that this function is the inverse function, right? So there is an axiom that says that for every x star x to the minus 1 equals E. So yeah, that's an obvious axiom that you want. So that's the inverse axiom right now. It looks like that. So what happens when we do the terms now? Well, when we define this A, or the set of terms, now we're going to have things of the form E, C, then we have A's and B's. A star B, the same as before, and everything you can do with that, but we also have things of the form A minus 1 star B, A minus 1 star B, star B minus 1, so on and so forth. All those terms. And now when we do the equivalence relation, we're allowed to use that axiom. And actually we have also the axiom that x minus 1 times x equals E. So what happens when we take the quotient? What do we get? What set do we get when we do the quotient? Because now, if you have something like A star B inverse star A inverse, I don't know, this is going to have an inverse, right? Because if we take this one times the same thing, A star B inverse star A inverse inverse, we have an axiom that essentially is going to be able to prove that this equals E. So this is going to follow from gamma that this equals E because of the inverse axiom that we have right here applied to this term. So now everybody has an inverse. One thing you can show to figure out what are these elements going to look like is that this guy here, A star B inverse star A inverse can be written as by inverting each of the elements and flipping the order. A star B star A inverse. And also, since we have associativity, it doesn't matter where we put the parentheses. So we get that every element is going to be of this form. Of every term, every closed term is going to be equivalent to what is called a word using the letters A, B, A minus B, A inverse, B inverse. I don't know, something like A, B inverse, A inverse, B, A, B inverse, A, B. That's a word. So what I mean by this is a shorthand for the word A star B inverse parentheses star A inverse parentheses star B star A. You guys get the idea, right? So the bottom one is the real term, but sometimes when you talk about free groups, I don't know if you heard about free groups, they are defined as these. These are defined as words that you can write with the letters A and B and A inverse and B inverse. And you have the property that, for instance, if in your word you have something of the form B, B inverse, A inverse, let's say B, then B inverse, then you will get that these two cancel out and you get an E, and an E cancels out because an E is nothing. And then once those cancel out, these two cancel out, and then you end up with those two together. So you get with A, B inverse, A inverse, B, A, B inverse, B inverse. That one comes there. Okay, so those are that's what it's called the free group. Everything you can write with this. The E's don't count because they can cancel. The inverses, when they are next to each other, they cancel, and that's the object we have. And what we get is a group. In this case, we get a group of words. It's a group of strings of symbols that is called the free group with two generators, A and B. So that's what you get when you do the set of terms and quotient by this equivalence relation. Let's look here at what happens when you do the field axioms. And now you have 0, 1, plus, times, minus, and inverse. And let's suppose that inverse of 0 is 0. Just doesn't matter because it shouldn't have a inverse 0, but the functions are supposed to be defined everywhere. So let's just do that. What do we get? What do we get when we do the field axioms and these? It's a good exercise for you guys to think. We are gonna get, let's start writing all the terms that we can get. So we can get terms of the form 1 plus 1 plus 1 plus 1. All the natural numbers we can get like that, right? So we can define, so these are gonna be terms that are gonna correspond to the natural numbers. We are gonna have terms of this to the minus 1, so that's gonna be inverse of a natural number. We also have negatives. We can use negatives, so we have all the negatives. And we can divide, so we can define n over m, right? That's going to be 1 plus 1 plus 1 n times divided by 1 plus 1 plus 1 m times. And by dividing, I mean multiply by this inverse. So we don't have, these are all constant, these are all closed terms. They only have no variables, they only use the constant 1. And you can add, divide, multiply, take inverse, take negatives. So what you're gonna get is that for every rational number there is gonna be a term. Right? For every rational number you can write a term like this. There are many terms, right? Because you're gonna have the term 1 plus 1 plus 1, and you're gonna have the term 1 plus 1 plus 1, for instance, for the number 3. But if in your field axioms, you can show that these two are equal, right? So your field axioms can show these two are equal. So when you do this equivalence class and this quotient, these two become equal in the quotient. So you're going to have that these are equal. And then essentially you're going to have that everything that you get is exactly the rational numbers. And no more. So everything can be represented as a rational number. So you're gonna get that m gamma looks like the rational numbers, which is a field. So that's pretty good. You actually get a field in this case. Again, it's important that you have the minus this function, the inverse function -1, so that you can build a term that corresponds to the inverse. Otherwise, you cannot build the terms that give you the inverse. Okay, so with closed terms, in this case, you just start from having the field axioms, you're going to build the field of the rationals, because those are all the terms you can build. Cool. So we have been using the fact that E is an equivalence relation, and so it's time for us to prove there is an equivalence relation, so that we can actually make sense to do this quotient. So this is is quite easy, I guess, because we kind of did it already. Well, we didn't do it, but we stated it. So equality, when we say this equality is a congruence relation, we meant that out of just the logical axioms, without any assumption, we can show all these things. That for every x, x equals to x. That for every x and y, if x equals y, then y equals x. And we can show that for every x, y, and z, then if x equals y and y equals z, then x equals z. So these things you can show from nothing. And now, what do we have? Well, let's do, I don't know, let's do just transitivity, just to see how it works. So let's suppose that we have S is related to T, and T is related to R, right? And S, T, and R are closed terms. We want to show transitivity, so we want to show that S is irrelated to R. Well, so what does it mean that, so what we know from here is that gamma can show that S equals T, and from here we get that gamma can show that T equals R. We know from the previous slide from last week that gamma can show that for every x, y, and z, if x equals y and y equals z, then x equals z. Using the axiom of instantiation of these for alls, we can like replace the things for all. Like we can replace x for s, the y for t, and the z for r. We get from here that x equals t and t equals r imply s equals r. Right, so this is doing the substitution and using that axiom with the for alls when we replace the for alls. And from now, from these ones and this one and this one together, just because of tautology, that these three tautologically imply that gamma proves S equals R, and therefore S is irrelated to R. Okay, so that's what we wanted, right? We started with this related and we end up with this, so that means that the relation is transitive. And of course you do the same for reflexivity and for symmetry, and that's how you get that it is an equivalence relation. It's going to satisfy those two. So this E on the set is an equivalence relation on the set of closed terms. Okay, so that means that this definition actually makes sense. We can take the quotient. In case, so once we have an equivalence relation, in case you don't remember, now we can do it formally. This here means the set of all equivalence classes for S a term in a closed term, where this, which means the equivalence class of S. What is the equivalence class of S? Is the set of all the T's that also belong to this set of closed terms, such that S is related to T. Right, so if you remember, the equivalence class means the set of all the things that are equivalent to this S. So the equivalence class has the property that S is related to T if and only if the equivalence class of S equals the equivalence class of T. Right, because they have the same things that are related to them. And so now, when we look at equivalence classes, what things that were equivalent before now become equal, right? So equivalence becomes equality. So that's why this quotient is good, because things that were before, these terms were different terms, but they were just equivalent under E. Now, when we look at the quotient, they are the same object. These equivalence classes of these terms, they become equal. So that's what we want. That if we can prove two things are equal, we want to make them equal. Good, so we have that given a vocabulary, we can build a set of closed terms. If we have a set of sentences, we can look at what are the terms that this set of sentences prove they are equal, and then we do the quotient kind of essentially to make them equal. So that means we have a method now to build a structure essentially from a set of sentences and a vocabulary. We have to do a few things. First, we have to make it into a structure. This is not a structure, this is just a set. We would like first to make this into a tau structure. And then we want to ask whether this tau structure is going to satisfy all these sentences that we want. And actually, as we saw already, it doesn't always. So there is more work to be done. But we'll continue in the next video.